Everywhere in the world today there are diesel engines, moving goods, moving people, moving earth. Today's diesel engines are sophisticated machines which give excellent power characteristics with low emissions and low fuel consumption. Cummins Turbo Technologies designs and manufactures its range of Holset turbochargers specifically focusing on the commercial and industrial market sector. The purpose of a turbocharger is to compress the air flowing into the diesel engine, squeezing more air into a cylinder. The engine burns air and fuel to create mechanical power. The more air and fuel it can burn, the more powerful it is. A turbocharger comprises a turbine and a compressor connected by a shaft supported on a bearing system. It is driven by the waste energy from the exhaust gas. The exhaust gas is guided into the turbocharger by the turbine housing. The energy in the exhaust gas turns the turbine. Once the gas has passed through the wheel, it leaves the turbine housing via the exhaust outlet area. Exhaust gas temperatures are up to 760 degrees Celsius, which means that high resistance materials are needed in the turbine wheel and housings. The speed and load of the engine determines how fast the turbine wheel spins. If the engine is in idle mode, the wheel will be spinning at minimal speed. As more gas passes through the turbine housing, the faster the turbine wheel rotates. At full speed, the turbine wheel can rotate at over 150,000 rotations per minute. The compressor wheel is connected to the turbine by a forged steel shaft. As the turbine wheel spins, the shaft powers the compressor wheel. Air is drawn into the compressor housing through the wheel and is compressed as the blades spin at a high velocity. The housing is designed to convert the high velocity, low pressure airstream into a low velocity, high pressure airstream at the outlet through a process called diffusion. Air enters the compressor at atmospheric temperature. However, it leaves the compressor cover at around 200 degrees Celsius. As air temperature increases, its density decreases, thus even more air can be forced into the engine if the air is cooled after the compressor stage. This is called intercooling or aftercooling and is achieved by cooling the air either with water or air. The forged shaft is held in a bearing housing. The turbocharger bearing system is lubricated by oil from the engine. The oil is fed under pressure into the bearing housing through to the journal bearings and thrust system. The oil also acts as a coolant, taking away heat generated by the turbine. The journal bearings are a free-floating rotational type. They float on a film of oil between bearing and shaft or bearing and bearing housing. The bearing clearances are very small, less than the width of a human hair. At both ends of the bearing housing are oil seal rings, often called split ring seals. These rings help to ensure that the oil does not leak into either the compressor or turbine housings. To increase the power from an engine, you can increase the size of the engine or increase the mass of the air burned in the cylinders by using a turbocharger. As altitude increases, air density decreases. At higher altitudes, the turbocharger wheel rotates faster, which increases the airflow to the engine. This turbocharger speed compensates for the density decrease, thus maintaining power to engine, where a non-turbocharged engine would suffer power loss. The benefits of turbocharging are increased engine power output, improved fuel consumption, improved emissions, altitude compensation. To improve transient response and low engine speed performance, it is desirable to control the turbine stage size. This can be controlled in two main ways. Wastegates bypass exhaust gas around the turbine using a valve in the turbine inlet, controlled by compressor outlet pressure. This limits turbocharger speed at high engine speeds and loads. In doing this, it reduces the boost pressure attained at full speed, full load, and allows the engine to develop more boost at low engine speeds. As engine speed increases, the wastegate valve begins to open at a preset boost pressure. This has the effect of increasing the size of the turbine stage. Holset wastegate turbochargers are engineered for superior durability and reliability. They are the premier choice for heavy-duty applications. A more effective, though complex method uses a turbine stage that is automatically varied while the engine is running. This permits turbine power to be set to provide just sufficient energy to drive the compressor at the desired boost level wherever the engine is operating. This is achieved by varying the area of a nozzle, a set of guide vanes that control the flow through the turbine. The Holset Variable Geometry System, VGT, is unique in that the vanes do not pivot, but slide axially. This innovative approach ensures a high level of durability and reliability, essential for commercial diesel applications. Variable geometry turbocharging yields several benefits: good transient response, good fuel economy, increased useful engine operating speed range, enhanced compression brake capability, reduced engine swept volume and package size for a given rating. Control of the Holset VGT is achieved through pneumatic or electric actuation. All Holset turbochargers undergo rigorous testing at development to ensure they meet stringent performance and safety standards. Cummins Turbo Technologies works in partnership with the world's largest engine designers to ensure that our Holset turbochargers are performance matched to the engine, ensuring optimum performance and fuel efficiency. All our facilities around the globe are certified to Lloyd's Register of Quality Assurance worldwide quality standards. Our reputation for turbocharger excellence has created a sound base for our future business. We are clearly focused on the heavy-duty turbocharger market, thereby dedicating our resources to the specific requirements of this key market sector. Holset turbochargers, breathing life into your machine.